Thanks for coming. This is video 2 in the gravity series. It's taken too long to get to this video because of my original approach. I tried to do it live coding and it's just been a nightmare to edit that together. So I'm taking a different approach, and I'll probably finish the rest of the series with a different approach. So I'm going to try to get the rest of the videos out a lot more quickly. So in this video we're going to look at the gravity simulation in terms of forces. There'll be an element of the repulsion force when objects get too close, and then there'll be the gravity simulation. This will be done in a single job. The code is not very long, but there's a bit of theory, so we'll talk about the theory, then we'll talk about the code, and then in the description there'll be a link to the Local Digital website with the code as well, so you'll be able to see the code from there. Okay, let's get into it. So in the first video we discussed how if we know the distance between two objects, their different masses, and some strength constant, we can actually figure out the force that each mass, or it's the common magnitude, but a force that they both apply on each other, basically, equal and opposite. So this was the mechanism we discussed in the first video about how we do that. Now if we think about how we apply this in the overall simulation, we need to take a few steps actually in the calculation. So just taking for a given pair of objects, we need to do this calculation up here in terms of, now the vertical bars here, this is sort of more of a mathematic notation. So the bars here mean the magnitude of f, because f should be a vector. So if we take a constant which will be given and set in the editor, we have our two masses, that's fine, that's set in the editor as well, and then the distance, which is based on the position. So if we compute the distance, which we can do here with code looking like this, we have the two positions. Imagine there's an array of positions, and so we have an index for current and an index for the other, because we're comparing two objects, looking at two different objects. We can then compute a vector between them, and so the vector obviously has size, as in length, but also it has direction. Now for the force calculation we only need the size. So we need to use something like Pythagoras' theorem to determine the size, which is the hypotenuse in this case, by summing the squares of each side. Now because it's three-dimensional, actually there are three sides. Now the cool thing about Unity's mathematics library is that it will, if I take for instance the vector d calculated over here, and I do a d times d calculation, it will use single instruction multiple data operations to multiply the x part of the vector, the y part of the vector, and the z part of the vector in a single instruction. Right, so this calculation is very fast, and all we have to do is sum. If we have this variable, think of it like a temporary variable dist1, and that equals d times d. Now we have the x, the y, and the z parts separately multiplied, and all we have to do is add them up, and we get distance squared. And we can use that in this calculation for the force magnitude. Now because we also want to get a force vector, what we need to do is we need to calculate a unit vector, and then we can multiply that by the force magnitude. Now the way to get the unit vector is basically to take the distance d and divide it by the square root of the dist square value, and then we end up with a vector which is a unit length, and then we can multiply that by f, and we have, and then it basically scales that vector by however big the force happens to be, as determined by this calculation. And so that's basically how we calculate the force that they apply on each other. The next trick is that we need to loop through all of the objects and basically calculate for each object the sum of all the forces that are applied to each object separately. Now, we can do it as in this sort of matrix style. And if we do a for loop, we have an outer loop, let's say, where we're looking at the current. So we might have, so here we have an array of forces that we're going to fill in. We're going to sum into this array. We also have another array of the gravity settings component, or the gravity component, and that will have position as well as the other values we need to calculate, like velocity and acceleration and so forth. And it has the mass, most importantly. But the point is that because we know the position, we can calculate the force. We can go from, let's just think of these as the index values, A through E. So if we say that A is the current in the outer loop, A is the current, so it's like 0. And then we want to consider for all the other alternatives, right, all the other objects. Then, okay, the current one is A. Now remember, we're going to sum them up. So we start with A, and we compare A to A, and of course we can't do that because the distance is always 0, and that doesn't make any sense. It doesn't apply force to itself. So we kind of ignore that, and that's why that's grayed out. And you'll notice that B to B doesn't make sense, so it's grayed out. Okay, but we can calculate A compared to B, compared to C, compared to D, compared to E. Okay, and so we can then go to this array and we can say, well, okay, so let's calculate for A and B, and we can fill that in for B, let's say. And we can fill that in for A, because the force between A and B is applied on A and it's applied on B. Then we go to A and C, the force applied on A, and the same force is applied on C. Right, now the force values will be different for each pair of objects, right? So from A to C, the distance is different, and the mass of C is different compared to, say, B, right? So here the distance is, it's a different distance, and this potentially has a different mass. Even though the mass of A is the same in each case, it's the mass of the other objects and the distance to the other objects that changes. So each force that they apply to each other, exert on each other, that will be the same. So it's the same force on A and C, right? But it's common for those two. But then when you have to consider A and B, A and D, A and E as well, right? So we calculate these forces separately and we add them up. So when we go through this process, we'll find that we'll actually calculate the same pair of forces, because we're going to consider for A all the others, then we consider for B all the others, then we consider for C all the others, for D all the others, and so forth. And we realize that if we start with A and consider all the others, then we've already figured out the value between A and B once, and then later on when we start considering B as the current, then we'll look at B to A, which of course is the exact same force value. So what it means is we can figure out that these are really the mirror of each other, right? This line, the grade line, we can consider as the folding point, and they're really like the mirror. They fold onto each other. So that means we only need to calculate the area under this line, right? We only need to calculate these values and just sum them up in the positions, and that's it. We only have to do that once. Okay, so let's take a look here at the gravity force job. So this is the job that does the computing of the gravity force on all the objects. It actually does one other thing. It will also, just because, if they collapse and basically they just hold onto each other, the whole thing could get very boring very quickly. So at a certain point they will repel each other as well. So this applies all those forces actually. All right, so what do we have? So we have our structure, which is a gravity force job. Now I'm using I job, and the reason for that is because we need to go through arrays in basically in a sequence that we see fit, and we need to access things both read and write. So there's certain constraints for using I parallel 4 job, or some of the other jobs. So the I job basically means that this will operate in the background thread, and that still gives us good enough performance actually. Now this is something I like to do with jobs, is I create a begin method, and so instead of, now this code could be anywhere. It could be in a separate static class. It could be in an update method somewhere on a game object, mono behavior. But I like to put it here. I like to put the whole issuing of the job, right? The scheduling of the job in the job struct itself. And the reason for doing that is, if I want to change the job from being an I job, I parallel 4 job, or any other thing, then all that decision is in one place. And so elsewhere, all I need to do is say begin, here's any dependencies, here's the data you need, make it happen. And in one place, in one file, I control what kind of job it is and how the scheduling needs to work, and we just get it done. So that needs to be a static, so it's public static because it's going to be called from outside the struct, and of course it will return the job handle, because this will be a dependency for another job in a chain. Okay, so then we have the execute, which is part of an I job, and then we just have these 2 methods that it calls. And so the reason for using, basically I like to use a clean code approach. It probably could even go a further, it could definitely go another layer further in this, but the idea is to try to name things instead of using comments. Okay, so zero out forces, what does that do? Because we have an array of forces, and we're going to add them up. So we're going to start from essentially no forces to the sum of all the forces for all the bodies exerted on them from all the other bodies. Right. So the first thing we need to do is zero it all out, and then go through a process of summing them all up. Okay. So that's what the zero out forces is for, and that'll be further down. The compute forces is obviously the thing that says, okay, let's figure out what the forces are for everything. And that's interesting. I could get rid of that bit of code. How about that? I like Visual Studio and it's highlighting of unneeded code. Alright. How about that? Alright, let's do that. Nice. Okay, so what are we doing here? Basically, for all of the objects, right? For all of the objects, so we have bodies and we have forces. So bodies are this is the main array here. Bodies here is the array of the gravity components. So this has the mass, the current position. It also has velocity and acceleration. But right now we're just worried about position and mass. Okay, so here. So we're basically saying for the current, so this is just like the diagram earlier, for the current, we're going to take the index of current from 0 through to the end of the number of bodies, and by the way, we are assuming that the bodies and the forces arrays are the same length, and if they're not, that's going to be a bad thing. Other, so the index of the others will go from 0 to basically the number of bodies, and then only when the current is less than other do we actually calculate the force. So this is to do with that matrix thing and the line going through it. So if we look up here, I have the comment. So less than means that if I'm currently looking at less than is the area under the curve, basically. I could go with greater than, and that would be the area above the curve. Either way is fine. So what I mean by area under the curve being this line here that's dashed out. And so that just means that, for instance, if I'm currently applying, maybe I lied. Anyway, it makes more sense to start from 1 because 0 doesn't do anything anyway. So if I'm currently considering 1, yes, so where other is less than 1, that would mean 0, we would apply forces. Where 2, we would apply it to 0 and 1, right? So that's what's going on. And it actually means that the other side is being avoided, not considered. So just to be clear, if I had not equal here, then I'd be doing both sides, right? Both mirrored sides, both mirrored triangles out of that matrix. If I do greater than, then I'm doing the right-hand side. Less than, I'm doing that sort of left-hand side. That's all it means. Calculate force. Okay, calculate force here. So this is where we do the magic. So here we take the position of current versus position of other, and we subtract it to get a vector. We want to get the square of that. So the beautiful thing here, this is using Unity's mathematics to essentially square the x, y, and z parts. So that will do that in a single instruction. That's super quick. And then what we do here is we sum them up. And now we have, in terms of Pythagoras' theorem, we have the distance squared. It is squared. We have the distance squared, basically. All right. Now, what we're going to do here is we're going to find out whether this test is about whether we should apply repulsion or not. So basically, if we have a repulsion threshold, which is a distance, if we square that, we can compare that to the distance squared. And this is just a float, so it's just a number. If the answer is that it's smaller, then we should definitely do a repulsion force. So this is actually a collision detection in the job system, right? This is literally a collision detection. So if the two are smaller than this threshold, we say, okay, you have collided. For all intents and purposes, this is a collision. Now repel each other. Okay. And so the way, because this is the ternary operator we have here with the question mark, so if this is true, then repulsion force will be applied. If it's false, then gravity force will be applied. That's how that's read. Then here the next thing is to figure out, this is the force magnitude, like how big it is. This gives us basically for a unit vector, which we calculate in the next function down here. We get a unit vector, so given any two positions rather, based on the distance between them, going from one to the other is a vector, like it has direction and magnitude. We want to make it a unit vector, which means the magnitude is 1, but it still has the same direction. And then because it's a unit vector, we can multiply it by the force, and we now have a force vector that is the right size. Okay, so we are getting that unit vector by making this function call below. And to do it, we have to supply the positions and the distance squared. And then for that unit vector, we multiply it by the force value. And now we have a force vector. Okay. And then basically, this is where we sum into the forces array. We say for whatever is the current value of, so for the forces array, for whichever is for the current, add this new amount to it. For the other, we do the subtraction. Now because it's a vector, that means it's the same amount but in the other direction. Subtraction, because it's a vector, opposite direction. Equal and opposite forces. So that's what this is doing. So at this point we have applied the forces, and actually the work is basically done. And the rest here is just utility. So this is the unit vector formula as an expression body method. So literally just taking the two positions, dividing by the square root of the distance squared. So that's because it's the distance is squared, we square root it to get just the distance. We had to square root it somewhere. And then for the gravity force, this is the Newtonian physics, classics physics formula, where you take G, gravity strength constant, multiply it by one mass, multiply it by the other mass, divide by the distance squared. right? Straight out of the physics book. Repulsion force, what I've done here is I want the force to be stronger where the distance is smaller, right? So I've just like gravity has an inverse square law, which means divide by distance squared. Basically doing the same thing here, just to make sure, because in this case we're dealing with really small distances, it's possible that it might be 0. So by putting 1 plus, that just protects it from being 0. And this is just some base, it's a constant up above actually. So that value could be changed. If I want to, I could make this something that could be edited in the inspector and actually pass it in as another begin value. But I haven't bothered. Okay, and this is just that function that zero outs all the forces. So that's it. The whole thing's done in 100 lines of code. We've figured out all the forces for all the objects pretty efficiently, and then we're ready. After this job is done, then we're ready to have the subsequent jobs in our pipeline of work to then compute acceleration, then velocity, then position, and then we can update the frame. Okay, so that's what this code does, and that's this session. Thank you so much for watching the whole way through. That should be worth extra points. If you found this interesting, helpful, please share with other people that you might think would find this interesting in terms of how to write jobs for Unity using the C# job system and doing things like physics and physics simulations. Also, it'd be fantastic if you could subscribe if you haven't done so. I'm going to do more on the job system, and if you would like, if you happen to enjoy it, please do like. You must have. You've gotten the whole way through, so please like. That'd be great. And if we can get a heap of likes, that would really help. So I'd really appreciate that. So soon some things should pop up showing you other things to watch in case other material and videos that I've done that you might find interesting. So thank you for watching. Oh, and also don't forget, in the description below you'll find a link to the code, so you can obviously copy and paste that and put that into your own project. And it'll be just this class that we've covered now, or this is struct, really, the job. But what we're going to do is for each step, each series, each video in the series, there'll be a new bit of code along the way, so keep an eye out for that. Thanks.